All right. So one of the things we have recently finished talking about is LP spaces, and we looked at various properties of LP spaces. So we found that LP spaces are Banach spaces, and then after that, last time I spoke very briefly about limit theorems, and just kind of mentioned that they play a big role in probability. We talked about a couple of different types of limit theorems there are. So there are things like laws of large numbers, and there are central limit theorems. So, and last time what we did is we saw a simple example of a law of large numbers for L2 random variables. That's something we finished last time. We, of course, I'll move over to the iPad screen and then just briefly review this. But let me just announce what's coming next. One of the next orders of business is to talk about conditional expectations. So you're already familiar with the idea of conditioning, right? You're familiar with the idea of talking about probability of A given B. The idea is that probability of A is just the probability of A, the likelihood that A will occur. But what is probability of A given B? Well, here some side information is available to you. You have been told that B has occurred. And based on that, you want to calculate what is the probability that A has occurred. Now you can talk about conditional probabilities, and also for random variables, you can talk about conditional expectations. In other words, if you have random variables X and Y, you could talk about the expectation of X, which is just the average value of X. Another thing you can talk about, which is different in general, is the conditional expectation of X given that Y has taken such and such value. Okay, so what the next order of business is to talk about conditional expectations. Since, of course, this is a course in measured theoretic probability, we'll be doing it in a relatively abstract setting. So the topic that we'll tackle next is something called conditional expectations. One of the things that happens in measured theoretic probability is that you first define conditional expectations and then define conditional probabilities in terms of conditional expectations. So this is maybe a little different from how it was in probability when you learned it at the undergraduate level. Now it turns out that to do this whole conditional expectation business, you need some results from measure theory. In particular, you need something called the Radon-Nikodym theorem. Radon-Nikodym theorem has to do with taking derivative of one measure with respect to another. So what we'll do is we will state the Radon-Nikodym theorem. I will not prove it. I will probably prove a little part of it, and then we will use this Radon-Nikodym theorem to talk about conditional expectations. Okay, so without further ado, let me start. Let me go ahead and turn off the camera, and let me switch over to the iPad. Oh, wait a second, sorry. I forgot to do something. One more step. All right, so is the iPad screen visible? I think it should be visible. Well, I'll take that as a yes. Okay, so what we did last time is we talked briefly about limit theorems. So we said limit theorems play a central role in probability. There are several types of limit theorems. So there's law of large numbers, there's central limit theorem. Now, as we said last time, there is no single law of large numbers. There are many things which all are described. So I don't know, if you want, you can think of law of large numbers as, I don't know, like Barfi, and central limit theorem as ice cream or something, okay? They don't taste as good, but there's no one kind of Barfi, but there are many kinds of Barfis, right? But all the Barfis have something in common. Ice cream, again, has something in common, right? So there is no the law of large numbers, there is a law of large numbers, and that has a particular flavor. And again, central limit theorem, it's a type of result. Okay. So we mentioned these two things last time, law of large numbers, central limit theorem. Law of large numbers would say something like this, that if I add n independent random variables, independent IID random variables, I divide by n. As n goes to infinity, this will converge to the mean almost surely. That would be a strong law of large numbers. If I look at a weaker type of convergence, such as convergence in probability, that would be a weak law of large numbers. And a central limit theorem involves a different type of convergence altogether. What we did last time is we saw that suppose I have xi, I going from 1 to infinity, which is a sequence of IID L2 random variables with mean 0 and some finite variance. And I take Sn to be the sum xi, I going from 1 through n, then 1 over n Sn goes to 0 in L2. We did this last time. Okay, and here we found that independence was an important thing that we needed. Okay, so now where are we going? We are going in the direction of conditional expectations. So let me just scribble a little bit. So before actually getting into the details, it may not be bad to talk about what are the things you're going to see. Okay, so we'll have a probability space omega fp, and suppose that I have x, which is an L1 of omega fp. So x is an integrable real valued random variable. And suppose that G subset of F is a sigma algebra. Now remember, we have said this before, that in probability, sigma algebras are a way of describing information. So if I say that an observer has information G, that means for any set in G, the observer knows whether that event has happened or not. All right. Okay, so here is the type of thing we'll be talking about. We'll have omega fp, which is a probability space. To talk about conditional expectations, we will need our random variables to be integrable. There will be no way around that. Okay, so suppose you'll have x, which is an L1 random variable on omega fp. Now let G subset of f be a sigma algebra. Now I'm going to think of G as information available to an observer. I will insist that G always be a subset of f. Now we'll think of G as being info available to an observer. What do I mean by this? That means that, let me just change this. That means that for any event B in G, the observer knows whether or not B has occurred. Okay? And then what we'll do is we'll define this quantity. Okay. What is this quantity going to be called? Let me also write this in orange actually. And this quantity is called the conditional expectation of x given G. Okay, so what you should think of this as follows. So when you see the symbol, how would you read it? I don't know. I mean, one thing you could say is you could write E of x given G. I don't know. I mean, I don't know. I feel silly writing this. But the point I'm trying to make is that this vertical line is read as given. Okay? So the idea is you're talking of the conditional expectation of the thing on the left, given the information to the right of the vertical line. Okay, so we'll define this quantity. What's going to happen? This will turn out to be a random variable. Okay, so the first thing you will note is that the conditional expectation of a random variable is going to be another random variable. Actually, let me add a little more detail there. The conditional expectation of an L1 random variable is going to be another L1 random variable. Okay, so E of x given G, whatever that is, however we end up defining it, is going to end up being a random variable. It is also going to end up being L1. How should you think of this, at least as far as your intuition goes? So think of E of x given G as best guess of x given the information G. Okay. Hopefully this becomes a little clearer as you go on, but if you're wondering intuitively what is this representing, you should think of this as giving you the best guess of x given the information G. Okay, so the tools we'll need. The tools we'll need are a result from measure theory called Radon-Nikodym theorem. Okay, what does this thing do? This talks about differentiating one measure with respect to another. Let's just fix the notation also. Talks about differentiating a measure nu with respect to a measure mu. Now I've gone ahead and, without thinking much, said that it'll turn out that just because I have a measure mu and I have another measure nu, there is no guarantee that I can differentiate nu with respect to mu. Certain things have to fall in place. Of course, we'll talk about that. But the big picture is Radon-Nikodym theorem talks about differentiation of measures. Okay. Of course, to even state Radon-Nikodym theorem, you'll also need this notion of absolute continuity. Perhaps I should have said this before Radon-Nikodym theorem, because you cannot state Radon-Nikodym theorem until you understand absolute continuity of one measure with respect to another. So nu with respect to mu. All right, so for the rest of the semester and perhaps the rest of the lifetime of this universe, WRT is read with respect to. Okay. This will save me a bit of writing. Okay. All right, so what are we going to do? We'll first talk about, let's say I have a measure mu and I have a measure nu. What does it mean for nu to be absolutely continuous with respect to mu? Then we'll see that if indeed nu is absolutely continuous with respect to mu, then you can define the Radon-Nikodym derivative of d nu, derivative of nu with respect to mu. Then the Radon-Nikodym derivative will have certain properties. Anyway, this Radon-Nikodym theorem will help us define conditional expectation. Now, of course, right now you do not see the connection, but as I said, hopefully it'll become clear. So the first order of business is to talk about absolute continuity. So let me just put this heading here. Okay, so I want to talk about what is absolute continuity. So rather than defining absolute continuity, I will start with an example where you do have absolute continuity, and then we will try and work backwards from that example. So here's what I mean. That omega f mu be a measure space. Okay, let f in L plus, remember L plus is the collection of non-negative measurable functions taking omega, in this case, to the closed interval 0 infinity, and define the mapping nu taking the sigma algebra f to the closed interval 0, infinity, note that the interval is closed on the right at infinity, okay? By nu of b equals the integral over b f d mu. Right? Now, of course, you remember what this is. This is just the integral over the whole of omega f times indicator b d mu. Okay, so I'm going to make this definition. This is something you have seen before, by the way. And what you saw when you did this is you learned that nu is a measure on omega f. Then we have, okay, so now I'm going to make some statements about nu and mu. These statements are things that we have done in class before. So let's see what are some true statements. So one, nu is a measure on omega f. Okay, I'm pretty sure we have proved this in class, or you have proved this on the homework or something like that. Okay, remember here f is non-negative measurable, and I'm defining nu of a set to be the integral over that set of f with respect to mu. F is non-negative measurable. You have shown this at some point in this lifetime or a previous one. You have shown that mu is a measure on omega f. I will not prove this again. A second thing you have seen is the following. I put a full stop here. Maybe I should not put a full stop. One, two. For any measurable g taking omega to r, such that the integral absolute value of g f d mu is less than infinity, we have integral g d nu equals the integral g f d mu. Okay, again, I'm pretty sure this is something we have done in class. Okay, so what's the story here? We start with omega f and a measure mu on it. We also have a non-negative measurable function f. Now, using this non-negative measurable function f, we define nu in this fashion. Nu of a set b is the integral over b of f d mu. Now we do a little bit of work and we convince ourselves that nu is a measure on omega f. Another thing you can convince yourself of is the following. You can convince yourself of, so now let me write a few things in quotations with a little bit of embarrassment. Okay? So basically, you feel like saying this. Right? When you look at this thing, it really makes you want to write d nu equals f d mu, whatever the hell that means. Okay, and if you believe that, then you're inclined to believe that integral g d nu should be the integral g f d mu. And again, you have not yet made this meaningful. Anyway, all this can be made meaningful. Okay, so the first claim here is that nu is a measure on omega f. Secondly, this type of formula does in fact hold, and here is a precise statement. So suppose g taking omega to r is measurable. And so basically what I want to say is that if g taking omega to r is measurable, this thing will be true so long as certain integrability conditions are met. Now, what are the typical integrability conditions going to be? The integrability conditions are going to be that the right side is integrable. Okay, if the right side has to be integrable, that means g times f has to be integrable with respect to mu. Now, you know that a function is integrable if and only if its absolute value is integrable. So for the right side to be integrable, what we'll need is absolute value of gf should be integrable with respect to mu. And there you go, that's the statement we're making. And a third important property is that if b in f satisfies mu of b equals 0, then nu of b equals 0. Okay, so what we're saying is if you have a measurable set and mu gives it 0 measure, you can be sure that nu gives it 0 measure. Now, you cannot go the other direction. Okay, just because nu gives something 0 measure doesn't mean mu gives it 0 measure. Okay, so here's what we're saying. So let's just check this. So indeed, if B is an F with mu of B equals 0, then what is nu of B? Nu of B is the integral over B f d mu, but this is just the integral of f indicator B d mu. Now, what do we know? We know that the measure of B is 0. In other words, we know that this thing is going to be 0 almost everywhere, right? Because indicator of B is 0 almost everywhere. And now if I integrate a function which is 0 almost everywhere, I'm going to get 0. So if mu of a set is 0, then nu of a set is certainly 0. Okay, any questions so far? All right, so now here's what we're going to do. Now remember here, we started with the function f and we came up with the measure nu. Now we're going to try and go the other way. In other words, we look at a situation where nu is given to us and we will ask ourselves, can we find a function f? So now the question we'll be asking is the following. Suppose omega f mu is a measure space. And suppose nu is a measure that somebody has given me. Can I say that there is a function f in L plus such that nu of b is the integral over b f d mu? Yes or no? Radon-Nikodym theorem says that under certain circumstances, the answer is yes. And moreover, that f is unique. Again, there's a little caveat because it's almost everywhere. That's where we're going with all this. So here we started with f, came up with nu. Now we're going to try and go the other way. So now the question we'll ask is, suppose omega f mu is a measure space. Suppose nu is another measure on omega f. Can you find a function f such that this property is true? Well, the answer to the question is going to be, if nu is absolutely continuous with respect to mu, then the answer is yes. So let's next give a definition of what we mean by absolute continuity. Okay, now I'm telling you that we have already announced what absolute continuity is going to be. This property, we will give it a name. So if mu of b equals 0 implies nu of b equals 0, then we will say that nu is absolutely continuous with respect to mu. So this thing that you can see highlighted in this red box is what we're going to take as our definition of absolute continuity. Okay, and Radon-Nikodym theorem is going to say if nu is absolutely continuous with respect to mu, then yes, you can find such an f. Okay, so let's state what absolute continuity is. Now remember here we're starting with measures mu and nu, okay? We don't have an f available to us right now. So let mu, nu be measures on omega f, all right? The measure nu is said to be absolutely continuous with respect to mu. Okay, how is this written? Let me written nu Okay, so this symbol looks like nu much less than mu. Okay, but that's not what it is. It is nu absolutely continuous with respect to mu, but you may have seen this symbol where somebody says 10 to the minus 5 is much less than 1 or something. Okay, so the measure nu said to be absolutely continuous with respect to mu, written symbolically in this fashion. If whenever b is an f with mu of b is 0, we must have nu of b is 0. Okay, so that's what absolute continuity means. As I said, we're just codifying this thing. All right, so let mu and nu be measures on omega f. I will say that the measure nu is absolutely continuous with respect to mu. I will write this symbolically in this fashion. If whenever b is an f with mu b is 0, then I must have that nu b is 0. In other words, if there is any measurable set which has mu measure 0, then it definitely has to have nu measure 0. All right, now let's just clearly, if nu of b equals the integral over b f d mu for some f in L plus omega, then nu is absolutely continuous with respect to mu. Right? This is not new. I've already written it down. It's right here. Right? Because we saw that if nu can be written as the integral of f with respect to some measure mu, then you have a guarantee that if I have a measurable set with mu measure 0, then the nu measure is 0. So basically number 3 here is saying exactly this. If nu of b happens to be obtainable in the form integral over b f d mu for some f, then nu is absolutely continuous with respect to mu. Now you can ask the question in the other direction. Suppose I know that nu is absolutely continuous with respect to mu. Does there exist such an f? Okay, so what this is saying is, suppose there is an f. Okay, suppose there is an f such that nu of b is integral over b f d mu, then you can be sure that nu is absolutely continuous with respect to mu. That observation was already made here. Now we're asking the question in the reverse direction. Okay, so this raises the question, so is the converse true? All right. So the converse would be, somebody has given me a measure nu, which is absolutely continuous with respect to mu, and now I'm asking the question, can I represent nu of b as the integral of some function with respect to mu? Yes or no? Anyway, this question is answered by the Radon-Nikodym theorem. So that's what the next item of business is. All right, so what does the Radon-Nikodym theorem say? So it says the following. So if mu, nu are sigma finite measures on omega f such that nu is absolutely continuous with respect to mu, then there exists a non-negative measurable f taking omega to the closed interval 0 infinity. Note that infinity has been included here, such that nu of any set b is the integral over b f d mu for any b measurable. All right. So this is basically the answer to the question. Is there such a function f? Well, if nu is absolutely continuous with respect to mu, then yes. Further, I claim that this function is unique in the following sense. Further, this function f is unique. Now again, by the way, this function is not, if you come into this with your BSc mindset, this function is not unique. But now you're thinking of your MSc or PhD mindset where you have learned measure theory. Okay, so, and when you've learned measure theory, you have been trained to say that, okay, if two things are equal almost everywhere, then maybe I should think of them as the same object. So here, when I say this function is unique, I do not mean that if f and g both satisfy this and f and g will always be the same. No, what I'm saying is that if g is another function which has these properties, then f and g must be equal almost everywhere. So let me say this function is unique in the sense that if G in L plus of omega. So again, this is not unique in the sense you would have studied in your BSc. Okay, this is a different sense of unique. In the sense that if G in L plus omega also satisfies nu of B equals the integral over B G d mu. In other words, if for any E in F, then F and G must be the same almost everywhere. Another way of saying it is that this radon this function F is essentially unique. In other words, if two people come up, if I come up with F and you come up with G and both of them satisfy these properties, then our two functions have to be equal almost everywhere. There is no way around it. Any questions with what is being stated? All right, so the assumptions are mu and nu are sigma finite measures on omega F. And this is a key thing, non-negotiable. Nu is absolutely continuous with respect to mu. If this is true, then there certainly exists a non-negative measurable f taking omega to 0 infinity, such that nu of any set is obtained by integrating f with respect to mu over that set. And further, this function f is unique in the sense that if you find another function g that does the same trick, then f and g must be the same almost everywhere. Any questions? All right, so now I am not going to prove the existence of this. I am, however, going to prove the uniqueness of it. But before I do that, let me make a few comments. Right, so we said that Radon-Nikodym theorem is about derivatives of measures or differentiating measures. Well, where is the differentiation going on? Well, here's where the differentiation is going on. Okay, so the function f above, this is of course if it exists, all right? I mean, if nu is not absolutely continuous with respect to mu, f is not going to exist. The function f above is called the Radon-Nikodym derivative of nu with respect to mu, and it is denoted, not surprisingly, d nu d mu. Okay. And maybe let me write as a proper fraction rather than doing this inlining. It's written d nu d mu. All right. Another bit of terminology. If d nu d mu equals f, we also say okay, so what I'm writing in this sentence is nothing new. I'm just introducing some terminology. Okay, so I'm saying that if d nu d mu equals f, one way to say that is f is the Radon-Nikodym derivative of mu with respect to mu. Another equivalent wording of that same fact is the following. We also say that the measure nu has the density f with respect to mu. Okay, so if you run into the statement that lambda has density f with respect to mu, what that means is d lambda d mu is f. Okay, so that's just another way of saying the same thing. Okay, so those are a couple of facts. So this function f, we are now giving it a nice name. We're calling this the Radon-Nikodym derivative. We're also giving it a special nice symbol here. And we're saying that Radon-Nikodym derivative is the same as density. So Radon-Nikodym derivative of nu with respect to mu is just density of nu with respect to mu. Okay, now, so we've done a bit of terminology. For a proof of existence, let's see where you should look. Now, you can see any of these places, okay? They will all have it. See, for example, you can look at the book by Royden on real analysis, he will have it. You can look at the book by Billingsley on probability and measure, he will have it. You can look at the book by Foland on real analysis, he will have it. And you can look at this book by Atreya and Sundar, titled Measure and Probability, they will have it. Okay, so the proof is standard, it is there, I do not want to cover it. Here are at least 4 places where you will find it. There are many other places where you'll find it. Any good, respectable book on real analysis and measure theory will have it. All right, but let's prove the uniqueness part. Okay, the point is that it would be nice to, of course, do the proof of existence also, but all these things take a lot of time. The uniqueness one can do without taking too much time, and I think it's a worthwhile exercise. So that's why we're doing this. So proof of uniqueness. Okay, so what do you have to do in proof of uniqueness? We have to say that Fg be in L plus of omega such that nu of b equals the integral over b f d mu equals the integral over b g d mu for all b in the sigma algebra F. Right? What do we want to show? We want to show that F and G are the same almost everywhere. Right, so what does the proof of uniqueness involve, right? I mean, the proof of uniqueness means suppose there are 2 objects which satisfy a certain description, prove that they are one and the same. If you do that, you have proved uniqueness. So that's what we're saying here. Suppose there are 2 functions f and g, both of which have this property. We want to now show that they are one and the same in the sense that they're equal almost everywhere. Okay. So here's what we do. We made this a fuss and said omega should be whatever, mu should be sigma finite, right? Mu and mu should be sigma finite. Let's put that to use. So what does sigma finite mean? If I say mu is sigma finite, that means I can take the whole omega, break it up into countably many measurable pieces. Each measurable piece will have finite mu measure. Similarly, if I say that nu is sigma finite, I mean I can take the whole of omega, I can break it up into countably many measurable pieces, and nu of each piece is finite. So let's start with that. Since nu are sigma finite, right? We have omega equals the union j going from 1 to infinity ej equals union k going from 1 to infinity fk, where ej, fk belong to f, in other words, they're measurable, and mu of ej less than infinity, nu of fk is less than infinity for all jk. Maybe I should also mention jk in the set of natural numbers. All right, so what is the idea? The idea is that mu is sigma finite. So since mu is sigma finite, you can find a sequence ej of measurable sets such that when you put them together, you get the whole of omega, and mu of each ej is finite. Similarly, nu is sigma finite. That means you can take the whole of omega, break it up into countably many measurable sets fk, such that the new measure of each fk is finite. Now remember, there is no reason that ej and fk will be the same, okay? If mu is sigma finite, it basically mu is sigma finite, so you're saying that there is a way to take the set omega and slice it up into countably many pieces such that something happens. Nu is sigma finite means you can take the whole set omega and slice it up into countably many pieces such that something happens. Now, that doesn't mean that the way you slice them up is the same. That's why we have two sequences, EJ and FK. For mu, you should slice up omega into E1, E2, E3, dot, dot, dot. For nu, you should slice up omega into F1, F2, F3, and so on. All this is making me think of cake, and I'm a little hungry, so perhaps I should not have talked about slicing. Nonetheless, we have to proceed here. Okay, any questions so far? So now, consider the countable collection EJ intersect FK, JK going from 1 to infinity. Okay, this is a countable collection, all right? Each set in this collection is indexed by two numbers, J and K. Now, note that mu of EJ intersect FK is finite. Can somebody tell me why this is true? Anybody? Well, y'all are definitely not getting cake then. Anybody? EJ intersect FK is a subset of EJ. Somnath, I'm sorry. I don't want you to miss out on your chance of having imaginary cake. Go ahead.
I am going, yes, sir. I am going to say that only.
Yeah, right.
It is subset of EJ.
Okay, so imagine you have been now given a delicious piece of chocolate cake. All right, so that's the idea. EJ intersect FK is a subset of EJ. So the measure of EJ intersect FK cannot be bigger than the measure of EJ, which is finite. So measure of EJ intersect FK is finite. Nu of EJ intersect FK is also finite for exactly the same reason. All right. Now what are we going to do? Now, by the way, this is a countable collection, right? Basically, okay. So let me dazzle you with my artwork. Okay, so all right. So what am I doing here? Other than creating art. So other than creating art, what I'm doing is I'm just showing you what all the J's and K's look like. Okay. So here J is 1, 2, 3, 4, dot, dot, dot. K is 1, 2, 3, 4, dot, dot, dot. Of course, you can write this in simply in terms of sets as the set of orange dots is simply n cross n. Now remember, this is countable. Okay. So, but right now it is written in terms of two indices, J and K. I don't like that. I want only one index. Can I do that? Yes, of course I can do that because there's a countable set. And you would have seen this at some point in your life. If you want to list all of these, you can say, okay, take this to be, I don't know, 1, 2, 3, 4, 5, 6, 7. You've seen this sort of thing, right? That diagonal thingy. The point is you can write this all out in a single sequence. And that's what I'm going to do now. So let this family be Gi, I going from 1 to infinity. Okay, so what did I do? I don't like having these two indices. Okay, so that I tell myself, since this is a countable family of sets, right? Because how many sets are there? Well, there are exactly as many sets as there are orange dots in this picture. And in this picture, there are countably infinitely many orange dots. Okay, and these orange dots can all be listed in some order, right? Maybe I could start there, 1, 2, 3, 4, 5, 6. You know that diagonal thing. As you can see, my artwork is greatly compromised. But anyway, the point is you can list all these orange dots. So list them in some fashion, and then list the corresponding sets. Gi, I going from 1 to infinity. Okay, so Gi is nothing but these guys. Okay, so if you take all the Gi's here, you'll get all these guys. This is much easier to write down and work with. All right. So what is a Gi? It is a set of the form EJ intersect FK for some J and K. Which j and k? Well, that depends on how you've done your ordering. But again, that is not of concern to us how you do the ordering. Okay, so now for any b in f, what do we have? For any b in f, we have, if I take the integral of b intersect gi of f d mu, right? What is this going to be? This is going to be nu of a intersect gi, which is also going to be the integral over, no, I'm writing a because I had a in my notes, but I want to stick to b, sorry. Equals nu of b intersect gi, but this is also going to be the integral of b intersect gi g d mu. Do you guys agree with this? Right, why is this true? Okay, so what we know is that for any measurable set, integrating g over that set, integrating f over that set gives you the same thing. And that same thing is nothing but nu of that set. Okay, this is as long as the second question is measurable. So now suppose I have b which is measurable. Each of these gi's is of course measurable. So nu of b intersect gi should be what you get when you integrate f over b intersect gi. And it should be what you get when you integrate g over b intersect gi with respect to mu. All right, so this is what you have. So, hence, for all b in f, we have integral over b, f indicator gi d mu equals the integral over b g indicator bi d mu. Do you agree with this? Okay, this is really not rocket science, right? You have learned that when you're integrating over a set, that is just the same thing as integrating over maybe a bigger set, but putting the indicator of the set you're integrating over inside the integrand, because you have seen this before. Okay, so now what do you get? By the way, we know that these guys are finite, okay? So let me just sneak that in here. There's no doubt that these guys are finite, okay? Because now what I'm going to do is in this equation, I'm going to do if left side equals right side, then left minus right is 0. And if I'm going to do left minus right is 0, then I better be sure that left and right side are finite. And they are finite because remember, this is why we broke up the whole omega into countably many pieces of finite measure. Okay, so hence, where are we? Hence, for any d in f, we have, what do we have? We have the integral over b, f minus g, indicator gi d mu equals 0. All right, and now what we'll do is we will recall a following result from measure theory. Let me write this in a different color. Recall result from measure theory. And what is the result I want to recall? If capital F and this is bad notation, right? Let me say capital H. If capital F, capital H belong to L1 of omega F mu, then the following are equivalent, right? Then integral over A F d mu equals integral over A H d mu for all A and F. This is equivalent to integral absolute value of f minus h d mu equals 0, which is equivalent to f equals h mu almost everywhere. Okay, so this is something we did when we were doing the real analysis part. We said that suppose you have two integrable functions f and h, okay? Then the following three statements are equivalent. F and h are equal almost everywhere. Second is that the integral absolute value of f minus h d mu is 0. Okay, these two are quite clear. The third thing is that for every measurable set A, integral over A of f equals the integral over A of h. Okay, and now we're going to use this result here. So, what do we have? So, we get f indicator gi equals g indicator gi mu almost everywhere. All right, that means for every I, if I restrict my attention to gi, then on that gi, f and g are the same almost everywhere. And now this is easily going to give you that f and g are the same almost everywhere. How do you prove that, right? Okay. Let me do the following. Thus, for every, so there's a bit of repetition. For every I in n, f indicator gi equals g indicator gi mu almost everywhere. Okay, so now what are you going to do? For every I, you throw away the bad set. What is the bad set? The bad set is where these guys don't match. For every I, you throw away the bad set. That is a null set. A countable union of null sets is null. Once you've thrown away a countable union of null sets, on whatever is left, f equals g. Okay. By the way, one of the crucial things, I don't know about crucial, but one of the important things here is that we had a countable collection of g's, all right? So what are we saying? Basically, we're saying you can throw away a null set. You can throw away a null subset of gi. One second. Excuse me. Okay, so here's a little more detail. This guy is 0 outside gi. This guy is 0 outside gi. Fine. Now inside gi, these two guys are equal almost everywhere. So there is some bad set where they are not the same. Call that set n sub I. It has measure 0, throw it away. Do this for every I. Let n be the union of all the n i's you've thrown away. Okay, the n you've thrown away has 0 measure, and on its complement, f and g are the same. In other words, f equals g mu almost everywhere, and that is exactly what we wanted to prove. All right, any questions with this? Questions? All right, so what we'll do next time is we will define what conditional expectation is. And in basically ensuring that conditional expectation, let me just stop sharing. Let me come back onto the screen. Right, all right. So basically what we'll do next time is we'll define what conditional expectation is, and we'll see that to actually make sense of conditional expectation, this Radon-Nikodym theorem does the job for you. Now remember, we stated this Radon-Nikodym theorem for sigma finite measures. So of course it is true for finite measures, and of course it is true for probability measures. All right, so let me go ahead and stop recording. Any questions?